and this aggregator is a small machine that just.
So does one worker has one adapter recursive circuit?
So all the workers, right now, all the workers, they can do everything. I mean, the thing is that there is very unbalanced. I put the same size, but actually we have 3 kinds of proofs. Now with the EIP 4844 we have 6, but this proof is very big. So, and these are, all the rest are relatively small. So at this point we could have like different kind of workers. At this point it's just a single server. So we have a single worker, and the aggregator can ask them, oh, you do this or do that. Then the difference is that generating this proof, it's about 2 minutes, and is about 10 seconds. Well, actually this is 2 minutes, all these together, it's less than 2 minutes. Okay? So this is a single, from the worker perspective, it's generated, so when you have a batch, actually you generate the output of the recursive. Okay, so this part is a single instruction. It's doing the 3 proofs. Then we have the recursive part, and this part, the final, these 2 last ones, it's also a single operation. So we have three operations: basic proof, aggregate proof, and final. Okay. And yeah, this is about 2 minutes. This is about 1 second.
Is it fair to assume that these workers in the cluster need to be like co-located very close to each other?
It can be. Actually, the cool thing here is that we are using for these provers, we are using spot instances. We started with Amazon, we are with cloud for political reasons, but yeah, but we can have both, or it can be volunteers. It can be anybody that just connects to them.
Ideally, you want that in the same region, right? Or not?
Not necessarily. I mean, the information that goes, I mean, you just put the input of the proof, which is small, and the output is a proof which is small. So it's not, they can be running, I mean, for example, here we have some development inside machines. Okay, sometimes let's connect that to the pool. So it just, and it's very flexible. Actually, we scale that. So we have a kind of a script that if the network gets a lot of traffic, then spin up more provers, and if loads the traffic, then they stop the provers. And we are using spot instances, which is this auction. You can do this relatively cheap. And yeah, and have been running sometimes 60, 70 provers in parallel. It's normal. Depending on the traffic on the network. It can be normally, normal cases right now, we lower it a lot. But maybe 2, 3 provers in general, smaller, depending on the traffic area.
Why start coming?
Because I made circle.
Why start coming?
Because I made circle. No, but it's Circom is very. So yeah, there is one trick, but so Circom gives you an arithmetization, and with arithmetization it's very easy to read and to test and to verify. With R1CS in Circom, you can convert very easily to Plonk like, and Plonk. Even if you are using phi, we are using Plonk. So the arithmetization is Plonk. At the end, it's a set of polynomials and are just relationship identities of those polynomials. Okay. So we have this conversion out of the box, and it's really, it's very, very, very flexible. And for creating these circuits, Circom is very intuitive and it's very clear. Also, for example, with the last improvements of Circom, we are using, for example, tagging. so that allows us, from the security perspective. Circom give us a lot of security. And there is some tuning around Circom that do a lot of security in there. So we are using extensively all these Circom tuning for and we have and the idea is that we have a kind of a template that given a build, so given a start, the template for we have a template that generates the Circom. So we have a template. We have a script that generates automatically the Circom. I mean, it's an automatically generated Circom out of a template that does everything, depending on the polynomials that you have, the scripts you have, it just adapts. It could be done with other things, I agree, but with Circom, it's, I mean, for us, has been working very well. Also, for the final, I mean, it's the same. I mean, we are verifying the stack, so the template is almost the same. I mean, it's different because so all these circuits, they work with multi-long spine field. The last one really is working with a BN spine field, so the circuit is different. But the structure, I mean, the idea of the circuit is so the template is the same. Okay? And yeah, I mean, this is, I mean, it's been working very well. Okay? And I'm joking a bit, but the fact that we made Circom give us a lot of knowledge. And in Circom, we added, for example, because this is a clockish, like for example, in Circom, we added this idea of custom gates. So in Circom, you can create a circuit that's, we call it a custom template, that cannot have constraints, and you're assuming that you are going to have a custom gate in the prover that's going to verify that. Okay? And so this for these recursion circuits has been worked very well. But could be done also in Halo 2 or in Plonky 3 or Plonky 2 or other tool. Okay. Again, I'm just saying what we did. Okay? What's better is just try it. And yeah, maybe there's something better. Okay, I don't know. I'm done. I don't know if there's somebody else.
Thank you, Jordan, for this. I mean, I learned about the question in a subjective way earlier, but this was very helpful. I mean, I didn't knew to this depth, although I wanted. I mean, it would have taken me around 34 years to basically get this. Yeah, it is. I'd like to invite Daniel to the stage and probably talk about the work that he's been doing with Scroll and Scroll with the recent upgrades. Also, thanks for the support for the sessions. It will not have been possible without.
All right, I'm not going to use this actually, but thank you so much. Okay, let me just do a little bit of housekeeping here. We've got 20 minutes left in this space. Okay, so I don't know how long someone's going to do a KZG talk. I'm trying to just kind of dynamically reroute what I'm going to talk about here. Our folks, I wanted to leave it as like a literal whiteboarding session where we're just going to talk about like, okay, what does it look like to have to upgrade a ZK EVM protocol from using call data now to like adapting and like how do we get gas prices down as much as possible. So maybe I'll start there. If anyone has questions, interest, or anything else, we'll make it conversational. We can dive into something specific. And then I'll just give myself a hard stop, and whoever's doing the KZG thing can tell me how long you're going to need, and we'll go from there. So, who is? Okay. Can you do your thing in like 10 minutes? Is that going to be fine? 10 minutes. Okay. We'll figure it out. Cool. All right. So basic problem set. basic familiarity with like the idea of rollups, so we're pretty good there. Similar to everyone else, you know, in the context of scroll, we're going to have a bunch of transactions coming in. We have an off-chain protocol. We have a smart contract on Ethereum that is going to then like take a bunch of those transactions that come in as that's coming in as call data, and then later on, that was a smart contract on a block. But later on, we'll then have a proof to pass on that is going to kind of like finalize the state transition from those transactions, right? Okay, so that's the super basics of where we're starting. Right now, everything is coming in as call data, right? We're using Ethereum itself as our data availability layer because we need to like have all the great things that that provides, censorship resistance, being able to sync your full node just from L1 data, all these nice things. And so in the past, right, we are submitting or committing to batches of transactions, and these batches under the hood, we're going to use this word called chunks. And then we kind of like context before, right? What we were able to do is in that smart contract, we were able to basically pass in all the raw transaction data, pass call data, and call data, you know, when you are using call data, your smart contract can then do stuff with that call data, right? So what it would do is it would find the boundaries in that batch of the chunks, there's some metadata somewhere in there, and then it would create hashes of every single chunk, and then store that in the smart contract, so that later on, when we go to verify this thing, the hashes of this transaction data can be passed in as public inputs alongside our proof, or rather references that we can pass in the proof, right? So that is how we constrain our proof on the L1 to the raw transaction data. That's how it kind of exists right now. Does that kind of make sense? Am I explaining this coherently here? Okay. Cool. So now the question is, with this upgrade to 4844 and side by side with that, you know, really the goal at this point, right, is like gas is too high. In the US, we have this presidential candidate that's going on this platform called "The Rent is Too Damn High." I feel like the gas price is too damn high. Anyways, we have really high gas prices. We have to figure out how to bring that down. Everyone's super excited about blobs. That is one way that we can do that. The other way that we need to be doing this for ETHs is going to be transaction compression, right? So these would be like the two things that I plan to talk about that we can kind of like get into the nitty-gritty about how to design a protocol to make sure that we're doing these things, but still making sure that it's sufficiently constrained from the L1 protocol smart contract perspective that we're able to do. Okay. So, does anyone have a preference which one I dive into? If I'm going fast here?
I'll say
Transaction compression? Okay, cool. Nice. The one I tracked less for, this is going to be good. What we can do in transaction compression. So right now we are passing in just kind of like raw transactions, right? Full information along with the signature as called, right? That is very expensive to be doing on the L1. So there's like lots of low-hanging fruit optimizations that we're exploring for the next hard fork, which I guess is the conversation here. One of the big ones is just finding the things that we don't actually have to include for us to be able to still reproduce the state, right? Because that's the goal of that L1 data. And so one of these things that can just be like inferred from proofs and everything else is like non-state data, right? It's not that sexy of a game, it's like 1 byte, but it's like still 1 byte less than call data for every single transaction. So we can drop nonces from what we commit on one side. Another thing that we can drop is we can drop signatures. This is actually kind of exciting because signatures are big, and we'll get into it in a second, but these are really hard to compress with generic compression algorithms. Like the entropy of a signature is very, very high. So because of that, these are very nice to draw. I don't know if it matters. Does anyone know how many bytes is in a signature?
66.
How much?
CSA 66 bytes.
I don't know. We'll say that. That's perfect. Okay, so we can drop nonsense in signatures. We can also do things like apply just generic compression algorithms, right? Things that you would use anywhere else. And so in that context, right, we get I think 2 to 3 by applying. Sorry, I can't remember the name of the compression algorithm that we're going to use. It's a great one. It's an open source C standard. I think is what we're going to be looking at. Facebook might have made this. Okay, so we got 1 byte from that, 66. My notes over there say 65 bytes from that. We get we can say 2.5 to 1 compression. That's the other way around through standard. And then things get more kind of exotic after that. So then you start looking at things right, you can start thinking about things like to and from fields from transactions, right? When you think about the number of bytes we use to represent a pub key or an account, right? That is a very, very big size. I wish I would have memorized the actual numbers here. But in actuality, we are not using the total space of the addressable space there is much, much larger than the actual number of addresses which exist, right? What we can do is kind of create mappings or essentially an index over all the addresses that we've seen, right? So, I have 0x ABC, and we can map that to 1, and then, DEF down here can get mapped to 2, and so on. So in our compression algorithm, we can start replacing very large things like addresses, which are also hard to compress and standard things, and replace those with indexes and just make sure that we're doing lookups as we're doing decompression there. Okay, I think these are kind of the major techniques. Jordy, am I missing one?
I think you make more or less maybe the distinguishing between stateful and stateless compression. Stateless compression would be just a fact, that is generic algorithm.
Right.
That the stateful, or even signatures are stateless, they are more complex. But for addresses and if you want to have a state that helps you to decompress, here is where you really can get a lot of good compression. But then we need to maintain this state for decompression and decompress.
Yeah, and I think maybe I don't know if this is a variation on that, right? But even these generic algorithms,
This is not, you don't do much of that. But this is what Apple is doing. I think they get 1.5, less than 2x compression.
Right.
It's 1.5 or something.
and you can when you're building these out though, right, there's a mode where it is just kind of learning as it's compressing over the data that you're feeding it, or that stream, to find patterns or whatever else. Or you can pre-train it on data so that it doesn't have to learn over those streams. So that is another thing that we're kind of looking
Have you
at.
done numbers of more or less what ratio of compression you want to have before the algorithms?
One more time.
So how much data savings after compression are you going to have? Have you done any numbers?
Yeah, so let me just pull that up because it seems more interesting than this. Okay, so our compression gain, we've done a lot of benchmarking, and so compression gain goes from nonsense signatures, just to give people an expectation. That is 1 to 1.07. So that is the 1.1. to 1.07. So like very tiny, right? 7% gain or something. Not that big of a deal. But when we get into doing, so we've tried compressing at the chunk level, and we've tried compressing at the batch level. Batch level is more efficient, and once we do Z standard on the batch level, drop the nonsense signatures, the maximum that we have seen is 4.22 without this, so up here. So basically these things right here, 4.22. And then if we also do indexing over the addresses, we've hit like 4.95. I think all of these are also in like, when you max out the compression level of these algorithms, which I don't know is going to be like something that we can sustain in the context of the sequencer as well. So these I think would be upper bounds of what we see when we decide to like.
And these are lossless compression.
What was that?
Lossless compression?
Yeah.
Yes, because all of these things, I guess that's the other side of this, right? Like this is something that is like a unique in the ZK context, right? But we're going to have to then decompress these things in circuit, right? So anything that gets done in the protocol side, we're going to have to like redo that in the circuit side as well.
So what's the approach for? Are you dropping signatures, or how are you compressing them, or?
So here, this is dropping the signatures for the data that gets committed. So there's like a few different ways to approach that. One is just to say, in the snark itself, you've verified these things. So
Okay. Yeah.
Maybe it gets published on an alternate DA that's like cheaper, you don't need for certain security guarantees. And then I think also that map is going to have to be published to the DA.
Right, because you still want to have, when you decompress the transactions on the L line, you want to have that map which signatures contain which transactions.
Yes, but we wouldn't be decompressing on the L1.
Okay, sorry, recovering.
Yeah, because really what we're just doing there is like attesting to that when it comes to the proof time. We're like, because that constraint there is like happens in the ZK proving side of it, and it's not going to be public input into that circuit. That is the 4844 part of the conversation. That it's not. Okay.
So for your information, the numbers, this is an approximation, it depends on the transactions and so on, but the numbers that we are managing need to be between 5x and 7x.
That you're saying right now?
The compression.
Okay.
Is so process there.
Can you special trick that you do?
Well, here, very much what you mentioned, we are not going to use this general purpose compression algorithms. We're going to be very much there. Maybe the biggest one, I mean, the ones that you didn't mention here is for the values. Values you can use again a floating point way of compressing values, especially if you are working with pen, if you're working with pen, with base 10. The users, you just play the fact that the users, they will send 5.745567 they send 7.4. They play small numbers. So if you compress them with floating point base 10, the values they compress pretty well. That's one topic. And the other is in this database, so the same way that you have address index addresses, you can have also the database of data, general data, which general change of units, and especially for a lot of algorithms that are reusing NFT. NFT has a value, but it is going to be used many times. So you can have an extra compression because it's a hash. With normal compression, you don't do anything. But the fact that you are repeating and that you are using the same value that are going to be many times, and this is very unique. So this gives us extra compression. So, but yeah, I mean, here of course, this is our estimations, and you will see it's a very sensible data, not just it's a random data, it's compression is going to be zero. So depends very much on the kind of transactions that will happen, and these are just estimations. But yeah, thinking about a 5x compression looks, that's pretty good.
Yeah, and I think I don't know, there's a lot of fun side topics here because this is all still just assuming we use post the transaction data and not state diffs. It's like one big kind of distinction. You want to follow up on that. And then the other thing is that figuring out how to then right, these numbers are not consistent per transaction. And then so on the protocol side, you have to start thinking about, well, how do we price this gas? Because we are passing on the L1 data feeds to those users. And so that's been a fun area of research too, right? It's not just how to get it as low as possible, but make it as fair as a protocol to be pricing it.
Just set a price for
Just okay, I think I went over the time that I told you I would take. So, yeah, thanks everyone.
Thanks, Daniel, for the session. I'd like to invite Nagu to probably help us out with KDDs.
All right, let's see how much I can skip the theory part so we can do some practical stuff. But I still want to show the slides so it becomes a bit easier. Give me 4-page notes. How much time I got? 20 minutes, 30 minutes?
To summarize, until they kick us out.
Until they kick us out.
That's it.
That's fine.
Can we do it another reason?
I mean, I send the KDCs too.
It's lunch.
Okay, because I thought originally I prepared, I'll actually derive KDG by hand for a small baby field. You can actually see all the finite field operations. But I'll try to skip on the theory part of it. Okay. So first, what do we, why are we interested in KDG? But there are two main reasons. So first motivation is almost all the modern snarks are basically they have one single formula. You have a functional commitment scheme plus you add a IOP, interact Morocco, essentially you get a that's pretty much the formula. Other big motivation is KGT is in Ethereum now. I'm sure you've heard of it. So it's different. This is already live now, so that's probably two big reasons why you should be interested. So with that said, I'll probably explain how KGD actually works. But before that, I'll give a basic setup. What do we need for KGD? First, a field. So we have field typically with a prime order P, and then this P is chosen such that